Thanks. Today, I would like to share with you a method for infer phylogenetic networks from trees. So this is a joint work with Niloufar Abhari, or Colijn, also Yufeng Wu. The phylogenetic tree has been used for over 200 years. But the phylogenetic networks are more useful than trees to describe and visualize the hybridization, recombination, horizontal gene transfer event. So therefore, the network model is being used more and more in the past 20 years. So in a network model, the tree node represents a speciation event. The reticulation node represents the recombination, hybridization, and other reticulate event. So we assume, so the reticulation node has multiple parents and a unique child. So the tree node has a unique parent, multiple child. In this study, we assume that every tree node has just 2 children. So this is a phylogenetic network model for the wheat-related grass species. So in general, so the space of network is much more bigger than the space of trees. So therefore, the network inference is more challenging than the tree inference. Currently, the parsimonious method work only for infer networks from less than 20 trees on taxon, if there are no clusters in common in the trees. So the maximum likelihood Bayesian method are even more slow now. Lastly, the interpretation and validation are also problematic for the phylogenetic networks. So I take the parsimony approach by work on this minimum phylogenetic network problem. So the input to this problem is a set of gene trees on the taxon X. The output is phylogenetic networks with the smallest size that display all the input trees. So by display, I mean this. So you have a tree, you have a network. So the network displays tree if the tree can be embedded mathematically into the network. In other words, you can remove some edges from network to get the tree after simplification. So the problem is still NP hard, but the nice thing about this approach is there are good tools for infer the gene trees. As I also mentioned earlier, this approach is faster than the maximal likelihood approach in general. This is our new approach. So we have 2 tricks. So the first trick is we focus on single networks, namely the tree-child networks. The second trick is we transfer the network inference problem to the shortest common super sequences problem. So this is a popular string problem in computer science. So the input is a set of strings. The output is a shortest string such that every string SI can be obtained from the shortest string by removing some symbols. So it's a very standard CS problem. Now we look at what are the tree-child networks. So in arbitrary phylogenetic networks, the reticulation node has a unique child. The child can be a tree node, can be a reticulation node. The reticulation node can have a multiple parents. So this is okay. The tree node has 2 children. So the 2 children can be both tree node, or one child is tree node, another child is reticulation node. The last case is the 2 children are both reticulation node. In tree-child network, we don't allow this, the last case. So in other words, so in tree-child network, so every tree node has at least 1 child that is not reticulate. So this is very important for the whole approach. Although the tree-child networks are special, the mixture graph output for the very popular program called tree mix often the tree-child networks. So here are the 2 examples from the literature. So now let's see the second technique, so how to transform the network inference to the string problem. So you have a tree like this. Suppose we have ordering on the taxon. So here we use the basic one, so alphabetic order, to order the taxon. Then with this ordering, we can decompose this tree into a set of passes. So this is how we do. So we first we consider the smallest taxon, A for this example. So we just move up from A to the root. Then we get to the first pass. Now we consider the second smallest taxon, which is B. So we move from the leaf B up, so until we reach the sum node in the first pass. So then we consider the third one, which is C. Again, so when we move up, we will reach the node in the first 2 passes. Then we stop. So on and so forth. Then this is how we decompose the tree into the passes. Then use these passes, we can also label the internal node with taxon. As you can see, so every pass starts from a unique internal node. So we just label the internal node with the same label as the ending leaf. So therefore, you can see that we label the purple, for the purple path, we label the starter node C, because the purple path also ends with C. So this is how we did. Then from these passes, we obtain the strings. It's very simple. On the path, then we have some labels. We just read the label from top to the bottom. We just ignore the first one, the last one, because the first one, last one is same, so we know. So most importantly, so we use this string, we can recover the original tree uniquely. So this is very simple because the string determines the passes uniquely. Then we use the label information to global the paths together. So this is so the observation. So we already showed that every tree has this string representation for every ordering. Then we can generalize this to the tree-child networks. But this only works for some ordering. If this works, then the representation also faithful. We can recover the tree-child network from this representation. So here's the idea. So we don't allow this kind of a tree node. So therefore, we tracing from leaf can reach all the nodes without passing through any reticulation node. So this is so therefore we can decompose this into passes. Then we can also label the tree node. The only difference is we label the pairs of reticulation node use the same label as the reticulation node. So therefore, from there, we can prove this relationship. So we have a representation for the network. Then we have a representation for the tree. Then we can prove the tree is displaying the network if only if the LTS obtained in the network is the super sequences of the LTS obtained in the tree for every taxa. Moreover, so if we have a set of trees, so the LTS obtained in the network is a shortest common super sequence of the LTS obtained for the trees for each taxa. So based on this theorem, then we can have this algorithm to reconstruct the tree child networks. So that we introduce variables to keep the smallest network. Then we just consider every possible ordering on the taxa. Then for each taxa, we just construct the LTS strings of each taxa in every tree. They use these LTS to compute the shortest common supersequences. They use the shortest common sequences to construct a network. So if the obtained network is smaller, then we just update the network variables. Then eventually, so we output the smallest one. But that's the exact algorithm is not fast enough if the n is bigger than 20, because 20 factorial is now a small number. So therefore, we have to modify the algorithm into this faster algorithm. So we replace the enumeration of ordering by sampling. Then also another bottleneck is compute the SCS for strings. Then we use the heuristic method. So this is the over method. Now we look at the validation of the over method. So we generate the random tree set. So using a reversing coalescence process to generate a network on T taxa, then we sampling the K trees from the network. Then we compare the over method against two methods. One published in 2015, another one published in the last year. So here are some statistics. So when the tree set were small, so each contained 10 trees on 20 taxa, so the three algorithms perform almost identically. So for the middle size tree site, so the over algorithm outperform the other two, in particular when the networks are complicated. For the large tree site, the one program could not finish within 1 day. So the prince can finish on some data site. The over method can finish in short time from less than 1 minute to 20 minutes for this large data set. Then also we did some optimality test. So the Van Answers et al.'s method also output the tree child network. You can see the over method output almost the tree child network with the same size, except two data set. Okay, so for this two data set, so the network output by over method is just a one node worth. For the Prince comparison is because Prince output arbitrary network by definition, the Prince performs better than over method always. So therefore, you can see in terms of optimality, our method is not good enough. So we also did some accuracy tests. So using the simulated sequences to reconstruct the gene trees, they use the gene trees use the sequence to infer the gene trees. Then we use the gene tree to construct network. So I will skip this. You can find the data from the full paper. And then also we use a real data set. So in this real data set, we have 247 gene trees over 13 grass species. Then we select 33 robust gene trees, and then we output this network. It contains 2 binary reticulation events, then 4 reticulation clusters. Then 3 clusters are consistent with the event reported in the literature. Then we also have 2 new events. So the network displays the 73 gene trees. They contain, on average, 73 node clusters for each of the remaining trees. So in summary, I just present a scalable method for the phylogenetic network inference. So this method is based on a very novel technique to me. We also have a version for weighted trees. So if the trees are weighted, we can output a weighted network. As you can see, the network has a very simple structure. It can be easily implemented into a parallel algorithm. This is because the computing tasks for different ordering are independent. For each ordering, the computing task on different trees are also independent. So we can do this in a parallel easily. Lastly, definitely more work needs to be done to make this friendly pipeline to biologists. Say, for example, we have to consider how to remove the effect of incomplete lineage sorting, then how to use the other information to improve the inference accuracy. For example, we know the gene sequences, then we may be able to improve the accuracy using the gene sequences. So the full paper is available in the archive. So also code is available. Okay, thanks.